What we're going to do now, we're going to take a look at the physical mechanisms of heat transfer, and the first one that we will consider will be conduction. So conduction is heat transfer due to atomic and molecular interactions. And the nature of conduction depends upon whether we're looking at a gas, a liquid, or a solid. And what we'll do, we'll begin with gases. And when we're looking at conduction in gases, we're assuming that there is no macroscopic velocity of the molecules or the atoms, that they're all kind of moving around on their own, but macroscopically, a bulk of them is not moving, because then that would be convective heat transfer. But to begin with, for gases, what we'll do, we'll sketch out. This would be from the kinetic theory of gases, where you have these molecules or atoms moving around. They all have different velocities, and they're all hitting into one another, colliding, and exchanging momentum in the process. So it is that energy exchange that is what is represented then by conduction within a gas. And there are different types of energy that can exist within molecules or atoms. So we can have translational energy, which would be the kinetic energy of them moving in a direction. They could be rotating. And you can also have vibrational. Now, vibrational would come in if you have, for example, diatomic oxygen, where you have two atoms of oxygen and they're connected through some bond. The vibration could be that bond where they're moving back and forth, or they could be rotating. And this is all covered in the area referred to as being the kinetic theory of gases. And through this theory, you can actually use these, construct models and predict some of the basic properties of gases. And so that is how we can have conduction in gases. Now, moving on to liquids. Now, liquids are similar to gases. However, with a liquid, there is a shorter distance between the collisions. And so we refer to that as the free mean path, or the free molecular path. And that would be the distance between collisions. So in the case of a liquid, that distance is shorter, and consequently, they don't have to move as far to have a collision. And then finally, the material that quite often conduction applies to is solids. Although you can have it in these other forms, but solids are usually the one that we're dealing with. And with solids, the molecules are in a more regular pattern, and they're fixed, and so they don't have the ability to move around as much. So we can have different types of lattices. You can have face-centered cubic, body-centered cubic. But typically when we're dealing with solids, there are two forms of interchange of energy. we can have lattice vibration, and we can also have electron motion. So lattice vibration is where the connection between all of the atoms or molecules would be vibrating. You can have these waves going through. And then in the case of electron motion, each of these atoms or molecules can have free electrons that are spinning around, and those can move through the solid. And those can also provide a form of energy exchange. And with that, given that we're talking about electron motion, the idea of a conductor versus a non-conductor, there's actually a relationship between electricity flow, and heat transfer. Okay, so what we have here is that non-conductors, so a non-conductor would be an insulator, they transfer energy via lattice waves alone. And if you have a good conductor, conductors transfer both through lattice waves or lattice vibration as well as electron motion. And the final comment here is that good electrical conductors are usually good heat conductors. So if you look at things such as copper is a very good electrical conductor. It's also a very good heat conductor. Gold, platinum, things like that. They're good electrical conductors, and they're also good heat conductors, usually the case. So anyways, those are the three different situations we can have for a gas, a liquid, or a solid when we're looking at conduction.